Okay. Okay. In this, it's during a typhoon. We call it a morak. During the period of the typhoon, and the accumulated precipitation is more than 2,000 millimeter in 3 days. So it induced a huge landslide and destroy one village, the Shaolin village, and about 400, almost 500 people are killed during this event. And you can find this is the picture before the event, and this is after. From almost the same viewpoint. Okay, you can find the mountain here. Okay, and the deposition is average deposition is more than 20 meter. So it's very difficult to imagine how it is. And let's have another view about. I have to close it. I have to close. I just continue. Okay, there's an aerial photo of the Shaolin area. We can find this is the Shaolin village, and the landslide was initiated from this area. Okay, and the total volume is about 24 megacubic meter, and the runner distance from here to here is about 2,700 meter, and the descending elevation is about 800 meter. Okay, and now we imagine if we would like to simulate this landslide. I think it's not a trivial work, and there are many challenges. So I just propose 3 main tasks. The first one would be we need an appropriate coordinate system to include the local curvature. And for the purpose of simulation, we also need an appropriate mesh system for the complex topography. And we have to consider if we would like to introduce the depth integration procedure or not, or the real 3-dimensional simulations. And the second task would be, what is the characteristic of the flow? I know many of you are experts in rheology, and I would like to know, we have to choose if we would like to use the continuum mechanics approach or discrete element approach, or we have to consider if it is a single phase material, or we have to use the mixture approach. Okay, they are open question. The third challenges will be at the bottom, the sliding surface, there could be entrainment, and at the runout distance, and there is the position. How is the mechanism of the entrainment or of the deposition? And once there is entrainment or deposition, we know that the basal surface become a non-material surface, and we have to introduce additional jump condition for this surface. And we would like to describe the evolution of the basal surface. Many things to do, but sometimes I don't know which one to begin with. And my recent work, sorry, I just skip the most difficult one is the rheology. You are the expert, so I just skip from them. My purpose is to propose a general description for such flows. So I concentrate our work on the coordinate system, and we hope that we can describe the erosion and the position process. Okay, there are many approach and coordinate system proposed by the other researchers. In our survey, we found that the coordinate system proposed by Bush and Vesta-Dickenberg have many superior advantages, so we adopt their coordinate system. We assume that the topographic surface is given in this way that z minus b, or z is equal to b, and b is the elevation from the reference horizontal plane, xy line on the horizontal plane, and z pointing upward against the gravity. Once we have the function of the basis surface, we can determine its normal vector, and we normalize it with this one. We compute this one, and the c is used to normalize this normal vector. And once we have this one, every vector, every position above the topographic surface can be decomposed by the projected point at the basis surface plus the distance above the normal direction. Okay, so we have the position vector. In this way, looks somehow ugly, but we know that this vector is function of time, is function of the space, and on this space we can introduce a two-dimensional coordinate, and normal is the third one. Okay, and this coordinate could be the projection of the regular grid from the horizontal. So we have projection on that. We obtain this one. It could be done in this way. So, and we adopt the coordinate transformation proposed by Professor Hui, and that because we know that R is the function of time and space, so we just use the partial derivative with respect to the different arguments, and we can include written them in, we can write them in a vector form, that capital Q times d lambda plus omega times d c. The capital Q is the local velocity of the coordinate system, and the omega is the Jacobian matrix. Here we know that dt is equal to d lambda, but we denote d lambda additionally to distinguish the two coordinate systems. And sometimes lambda is also equal to, you can see it's equivalent or quasi-equivalent to Lagrangian time in Lagrangian coordinate system, because in Lagrangian coordinate system you need the origin of the time. They could be of different origin. And in this transformation, we have the freedom to choose the coordinate velocity. If we choose capital Q equal to 0, we obtain the Eulerian description. If we choose Q equal to the fluid velocity, it's the Lagrangian description. And in our proposal, we choose Q equal to the erosion rate. In this way, our coordinate or the surface coincide with the basis surface and always deform and move. That's our intention, to do this way. Okay. I do not go into too much details about the transformation. There are many transformation formula. I just delete them. Okay. And because we would like to investigate the property or the feature of this formula, we just use a very simple material. Okay. And so we use the incompressible fluid. So this is the mass balance, and this is the momentum balance equation in general form. Here, Ij is the index for x, y, z for the Cartesian coordinate system, and if we have the others, we have also the other coordinate system is the terrain fitted coordinate system. We call it theta, eta, and xi, eta, theta, and they are covariant basis. And once we transform them into the Cartesian coordinate system. This transformation is unusual as what we have learned. You will find, okay, at first we have the J is equal to the determinant of the Jacobian matrix, and you find that the determinant that the partial differential of the Jacobian is equal to the spatial divergence of the velocity. And the second one is you can find in the momentum equation, we compute the Cartesian component instead of theta, instead of the terrain-fitted coordinate component, but with respect to the terrain coordinate system. And the advantage of this transformation is that the stress, the stress tensor behavior is similar to a vector behavior. And we can avoid the complicated computation for the Christopher symbol. Okay, and in this way. That's the first transformation. After that, we will introduce the depth integration and dimension analysis. Okay, and I just skipped this process, this tedious computation, and we obtain the equations. In this equation, we use incompressible material and isotropic normal pressure, and H is the flow depth, and you find it's very similar to shallow water equation, but only with respect to the terrain fitted coordinate system, and E is the deposition rate. Okay, I just use E in deposition rate. Okay, and we compute the momentum component in X direction instead of in Z direction, and pi is the momentum correction factor due to different shape of profile, different shape of velocity profile, and this term is the stress term, and this is due to the erosion. We consider the momentum loss due to in deposition, and S is the source term, consists of the normal stress from the basal surface and the drag force. And I just repeat this idea. The basic concept is actually normally we compute the average tangential velocity, but in our formulation we compute its X component of the tangential velocity. Why we do this one? Because if you have any erosion and deposition, the orientation of the basal, the tangential basal direction is changing. It will become complicated for you to determine it. But this term is uniform. Okay, not uniform, it's unique. You don't need to recompute it due to the change of the orientation of the coordinate. Okay, so far so good. After this, we begin to do our simulation. We implement this equation system with a non-oscillatory central scheme, and we consider one simple case. It's a shoot inclined part to horizontal part, and a finite mass flowing down and deposit here. The color indicates the flowing layer, and the light color indicates the deposition heap. And you can find that the deposition heap develops from the bottom to the top, from the front to the rear. Okay, in this, we just consider a very simple criteria for the deposition rate. We consider neutral angle. If the inclination angle, the partial inclination angle is smaller than the neutral angle, and the velocity is smaller than some threshold, we say, okay, deposition develops. Okay. So now we want to apply this formulation to the real case. Okay. And at first, we come back to the view of the area of the Shaolin village. We have the scar area from here, and the landslide flow was divided by one here, or ridge. We call it 590 height, into two streams. The main stream will be here. If the amount of the landslide mass is not so large, I think this village can be protected by the height. Unfortunately, the size of the landslide is so huge. Part of the mass overflow this height and attack this village. So, and from here you can find that the negative deposition is almost 100, or it's almost 80 meters deep. So I just show, no, how can I let it go? This one. Okay. So, okay. You can find the main stream go from here, and the part of the stream attack the northern part of the village. Okay, this and we need some evidence to support our simulations. So at first we have to determine the optimal friction angles in our formulation. The only one parameter to determine is the basic friction angle. Okay, and we, after our optimization process, we calculated the center deviation, and we obtained that the optimal friction angle is around 11 to 12 degree. They agree with the friction coefficient projection relation on the geometric constraint, and also to this numerical study from Dr. Stara. Yeah. Okay, and the total duration is around 2 minutes. That's our computational parameter, okay, for you. So I have to hurry up a little bit. So the maximum speed reaches about 50 meters per second. And we also check the transient volume fluxes. The maximum here volume fluxes is in this DD plumb section. And we also check this section to estimate the mass attack the village, or the village is around here. And we found that it's about only 7% of the solid volume flow through the village, but already destroyed. And we also have some field measurement to support our simulation. We perform the near surface magnetic survey is not our colleague, okay? And we found that the northern part, you cannot find the magnetic signals. That means all the artificial structures such as houses, cars, and something with steels or metals, you can not find anything here above. And there is a front magnetic, the signal front approximately here, and this front is approximately coincide with our flow boundary of 1 meter depth. So let me conclude. Okay, we propose a simple alternative formulation for the non-trivial topography, and we also perform the reconstruction for the Shaolin landslide catastrophe, and the result is supported by our magnetic survey. However, it seems to work well, but I have to say it's not perfect. Okay, there are still a lot to do. I just propose a formulation. Okay, the reality is an open question. The initiation, I think, if you check, if you can remember our simulation animation, there's something not so realistic in our simulation. Also, deposition. In this I have to say, for the Shaolin Village simulation, we turned off our deposition mechanism because I think my previous simple deposition rate cannot work in this simulation. Thank you so much.
Take time for one short question.
Yeah.
Yeah, please.
Okay, so judging from the complexity of your domain, I can see quite a few points that your curvature would be, let's say, not defined even. So that would make your Jacobian awful. Could you just explain how do you deal with these points, especially in this nice village simulation where I'm sure I can find several places where your curvature is not becomes infinite? Yeah, there, that's.
Yeah, here.
I mean, I see several points where the curvature becomes infinite here. So how do you deal with this problem in your Jacobian?
We have the digital terrain model, and we just project it onto we use this one.
No, but your transformation is based. Jacobian has to be well behaved. So even in this domain, your Jacobian behaves well.
Yeah.
That's interesting. Okay.
Just a quick question. I think you have a nice tool to quantify how much deposition rates will influence the runout compared to rheological difference.
Yeah.
So what do you think? Do you think the rheology matters more than the topography? Or do you think that the topography that will induce erosion or deposition rate will affect more the runout?
You mean the deposition rate?
Yeah.
I think rheology play more important one.
They're very important.
Very important.
So you
It's
would
my
rate
personal opinion.
more than.
Because I just use very simple erosion rate or deposition rate, just compare with this ad hoc assumption, and it does not work in our simulation. So I'm interested in this topic, but at this moment I have no answer about this.
Okay. So thank you for